Hey everyone, in this video I'd like to give a brief introduction to vectors. So for us in this Calculus 2 course, a vector is a quantity. So I'm going to give kind of a heuristic definition here, but it's a quantity that has both magnitude and direction. So it has a length and a direction. So magnitude here we'll think of as like a length or some kind of some kind of a numerical value. So usually it's going to be a length. So a magnitude and a direction. And so to be able to represent a vector, we have to be able to describe this vector in terms of both its magnitude and its direction. And there's a nice way to do this geometrically, which is to represent a vector by a directed line segment. So a line segment has a length or a magnitude, and a line segment also has a direction, right? So like I said, we will represent these vectors by directed line segments. Now, how do you give a line segment a direction? Well, essentially, you make it an arrow, right? So if I call this vector v, and by the way, we usually, in our text, our vectors are bold-faced. So rather than trying to write a really dark bold-faced v here, I'm just going to give it a hat, okay? And this is standard in mathematics. So this v with a hat represents the vector v, and this vector v is, again, represented by a directed line segment or an arrow. Now, how do you make an arrow? Well, you can look at this arrow and you can see that the arrow has at least 2 points, right? 2 endpoints. It definitely has 2 endpoints. And one of these endpoints is like the initial point and the other one is the terminal point. So one of them is the tip, the front of the arrow, and the other one is the tail, the tip and the tail. So here in this picture that I've drawn, P is the initial point, all right, and Q is going to be called the terminal point. And the way that I've drawn this, it looks like I've drawn it on the surface of the screen that you're watching. And very well could have, right? But it's possible, though, to draw a line segment. You can be in just a 2-dimensional space, like the surface of the screen, or you could be in 3-dimensional space, like we had an introduction to in the last lecture, or even in a much larger dimensional space. So for us, we're always going to think about our vectors living in either 2 or 3-dimensional space. All right, and so I'll write that down. Our vectors live in either 2 or 3-dimensional space. All right, well, let's talk a little bit about how we can represent this vector. So by the way, this vector is completely determined by these 2 properties, by its magnitude and its direction. And one thing that we can do with vectors is, I don't think I got enough of it there, one thing that we can do with our vectors is we are allowed to pick them up and move them around. All right, then we can kind of arrange them to be anywhere we want in our space that we're working in. Again, either our 2 or 3-dimensional space. We can place them wherever we want as long as we do not change their magnitude and direction. So this is a property of vectors that's called parallel translation. So we can parallel translate a vector without changing it. We didn't change, so I put that vector back pretty much where it was, right? But even if I left it somewhere else, it would not have changed it. Now, what it would have changed is the initial and the terminal point, right? So without changing it. So again, if we get rid, let me move it a little bit here. Let's say I move it over here. Well, now the initial and terminal points are no longer P and Q, but the vector is still V. Okay, so you're allowed to move the vector around. It'll change the initial and terminal points, but as long as you don't change the magnitude or the direction, then you have kept the vector exactly the same. So for this reason, well, yeah, okay, so I need to say a couple things here. But what we're going to do, let's think about our vectors in 3-dimensional space, and then you can go back to 2-dimensional space. So there's our R3 is our notation for 3-dimensional space. If you want, you can then go back and think about 2-dimensional space. But let's say we have our 3-dimensional coordinate axes here, our coordinate system, like we studied in the last lecture. I'll even give the negative portions. And let's say that we have a vector. I'm going to make this vector red. I'll put it out here. This is our vector v. All right, this vector has an initial point and a terminal point, right? It's an arrow or a directed line segment, you might say. And based on the conversation we just had, I am allowed to, as long as I don't worry about where the initial and terminal points are, I am allowed to pick this vector up and move it anywhere I want in space. It turns out there is one place that we can put this vector that makes it kind of like ideal to work with, and that is to put it so that its initial point is at the origin. All right, and similarly now if I have another vector, let's call this one W, and this one has initial point here. This vector is just kind of floating around out here. I'm allowed to pick this one up and move it around, right? And I can place this one so that its initial point is also at the origin. All right, and so what's the benefit of doing this, right? So the benefit is that if I'm allowed to move these vectors around and place their initial points anywhere, if I choose a point to put all the initial points, which I'm going to choose the origin, right, then I only need one more piece of information to describe these vectors. All right, so if we place the initial point of each vector at the origin, so of all vectors, let's just do this. I'm going to rephrase this. I don't want to say that we put this for all vectors because we are going to still want to move the vectors around. But if we put the initial point of a vector at the origin, then we're going to say that this vector is in standard position. So I'm going to give the vector a name v, right? So I'll call it v for a vector. This is in standard position now. All right, so this is going to be our standard position of the vector. And once we have our vector in standard position, then we can start thinking about how do we identify the vector in terms of the coordinate system that we just chose, right? The second you choose that initial point, you've taken a big step toward choosing coordinates. Now, I already have the axes here, right? Once you have axes, you have coordinates automatically. And so at this point, to describe our vector, when it's in standard position, this is the key, when it's in standard position, to describe our vector, all we need to do now is we need to be able to describe the terminal point of the vector, all right? So I'll write this down again. So a vector in standard position, SP, all right, is completely determined by its terminal point. This is an important fact. So this vector is completely determined by its terminal point. Now, the terminal point has coordinates, right? So scroll a little too far there. Let's say the terminal point of this vector v is p, and its coordinates are x1, y1, and z1. All right? Well, that point, p, is the terminal point of the vector v. So v and p are kind of closely related here, right? So the origin we usually call O. What we can say then is that v in standard position is the same as the vector that starts at O and goes out to p. The vector O, or the point O here, is the origin, right? And so the coordinates of P completely describe our vector V. And we can then write down coordinates for the vector. We can write coordinates for this vector. So this vector V can now be described by the same coordinates as P, the coordinates of its terminal point, x1, y1, and z1. But instead of putting them in parentheses, parentheses are reserved for points, right? So instead of putting them in parentheses, we put them in angle brackets like this. And so these brackets tell us two things. They tell us the coordinate, or three things really, 2, 3, whatever, either 2 or 3 things. So they tell us that the coordinates of the terminal point are exactly this, right? So x1, y1, z1, that's the coordinates of the terminal point. It also tells us that the coordinates of the initial point are 0, 0, 0, 0. It's the origin, right? That's what the angle brackets tell us. You can only write angle brackets if your initial point is the origin. And the reason I waver between 2 and 3 pieces of information, right, is because that in turn tells us we are in standard position. So the origin being the initial point, so initial point at the origin, that's the same, right, as standard position. So vectors in standard position can be represented by their terminal point just like this. So if this one's Q, and this vector Q is given by, say, x2, y2, z2, then our vector W can be, again, represented as OQ if we wish, or just in angle bracket notation, in component notation here, as x2, y2, z2 with the angle brackets. All right, so this is the standard, this is the notation for the standard position of a vector. Now, what we are going to have to do is we're going to have to try to find a way to describe our vectors that are not given in standard position by getting them into standard position. So let's go back to a vector that is not explicitly in standard position. So I'm going to draw the coordinate axes though. So let's say we have our vector, or our coordinate axes, x, y, and then z. And let's put a vector out here floating around in space that is built by connecting from one of these points to the other. Let's go in this other direction here. All right, so let's say this vector goes from P to Q. All right, we'll call this vector V. And hopefully now we're starting to understand that this vector V is related to P and Q the way I've drawn it here, but if I pick it up and move it around, P and Q are going to have to move as well, right? So let's take a look at this. So let's say that the points P and Q, we can't write down components for this vector right now because it's not in standard position yet, right? So let's say that the components for P are x1, y1, z1. That's the initial point of our vector. And the components for Q are x2, y2, z2. That's the terminal point of our vector. All right? And I want to try to write down what I called the component form. I briefly said I didn't write that part down, but the component form. I want to try to write down this vector V like this, right? Where it's just, it almost looks like a point, except it's got the angle bracket. So that's our component form or standard form. All right, so standard position leads to standard form in some sense, all right? So how can I do that? Well, I need to pick up this vector. Remember, I'm allowed to do this, right? Pick up this vector and translate it over to the origin, parallel translate. So in this case, I'm going to do this by actually, whoops. All right, so I need to copy and paste. I want to move it, but I want to have another copy of it that I can see. All right, so there we go. I'm going to pick up that vector, move it over here, so that now this is the same vector V. Remember, when you do this, you don't change the vector. Now I just have 2 copies of V, right? I just have 2 copies of V. So this vector V is now over here. It's got a new terminal point though, right? This point here is now Q. And it's got a new initial point. The new initial point is O, it's the origin, right? So this vector V can be represented as both the vector PQ in that direction or the vector O, I call this Q. You can't have 2 Q's, so we need another name. Let's call it R. Sorry about that. So, or it could be represented by the vector OR, right? But only the vector OR is the one that's in standard position. That's the only one that's in standard position. So that's the one that we're going to use to try to find the components. But to do that, we need to know what are the coordinates of this R. What are the coordinates of this terminal point R? All right. So what we can do then is we know that we need to move P to the origin. We know where the initial point is. The initial point is at the origin. So we can move this vector P, translate it all the way down here, and pretend that's a straight line. All right, it's almost parallel to the vector, so that was a bad choice of vector that I chose. But if we move that here, we have to also move the point Q over to R. So our point P gets moved to the origin, and our point Q gets moved to R. Well, how are we going to move the point P to the origin? We have to translate each of these, right? So we have to subtract x1 from the first component, the first position, subtract y1 from the second position, subtract z1 from the third position. That's how we get P to the origin. Then we'll have 0, 0, 0, right? So from P to O, here's how we do it. We take our x1, subtract x1. We take our y1, subtract y1. We take our z1, we subtract z1. Now we're at the origin, right? So we're at the origin. All right, let me get my highlighter out. This motion that we made, right, this subtracting in term by term subtracting here is like a motion. This is just a point right now. So this point is just a point, like I said. But this motion that we made is the same. We have to do the same exact thing for Q. That's how we're going to make sure that we don't change the direction or the length of our vector, right? And so to move from Q to R, the motion that we have to make is we have to take the coordinates of our x, right? We have to take x2 and do the same thing. Take away x1. We have to take our y2 and we have to do the same thing. Take away y1. We have to take our z2 and do the same thing. Take away z1. Okay, and so this is the coordinates of R. Well, if these are the coordinates of R, then that is exactly, right? This is exactly what goes in our component form up here. And so we can say then that the component form of our vector v is exactly the vector in standard notation or standard form that has these components, right? Terminal minus initial. Terminal minus initial. And this is how you remember it. Terminal minus initial. That's how you get your standard form components. All right, so terminal minus initial. All right, we're going to do some computations with vectors in the next couple of videos. To finish this video, I just have one more thing that I would like to say, and this is the kind of physics interpretation or physics way of representing vectors. It's not unique to physics, it's just the favorite way of the physicists, okay? So there are three very special vectors called standard unit vectors. So these standard unit vectors are called I, J, and K. And if you guys are in a physics class, you might have already seen these vectors, okay? So the vector I with a hat, it's a vector, right? In standard position, or standard notation, this is the vector that points 1 unit in the x direction and nowhere else. So over here, I'm going to plot these vectors. All right. In some ways, you might say that this is actually the more geometric way to represent these, but like geometers probably rarely use this actually. But this vector I, I'm going to make it red. The vector I points exactly 1 unit in the x direction. All right, the vector j, we can probably almost guess what's going to happen, right? The vector j points exactly 1 unit in the y direction and nowhere else. So just straight into the y direction, nowhere else. I'll make this one blue. So the vector j is going to be right here. This j stands for Justin. Just joking there. And then the vector k with a hat, and now we really know what's going to happen, right? This is going to go straight up in the z direction, 1 unit and nowhere else. So this vector k goes here. And now here's the idea. Let's say I have a vector v, a generic vector in space. All right, and I want to try to represent this vector. Well, we already know I can pick this vector up and move it to be in standard position, right? And so then what do I need to do? I need to be able to describe how am I going to get from the origin, the initial point, out to the terminal point, right? So what we can do is we can build our way out to this by doing exactly what we did and when we studied the three-dimensional coordinate system. So we need to find a way to get to this point, right? So we can start by going out, say, this far in the x direction. And then we can go, say, this far in the y direction. And finally, to finish this off, we'll want to go straight up this far in the z direction, right? So this forms our little path that we're going to take. And so whatever this distance is, let's call it x1, then we need to stretch our vector I by that much. So we'll talk about this in the next lecture, actually, in the next video about exactly what this means. But I'm going to say it now just so we have this all together. But we need to stretch this a little. So we're going to multiply our vector I by this much, okay, by x1. And then we're going to do the same thing with these other two. So this is going to be y1. And this one's going to be z1. And so these are just 3 numbers that we're going to regard as stretching factors for I, J, and K. And like I said, we'll return to this later. But what we can do is we can represent our vector v as the sum of stretching factor x1 times I plus stretching factor y1 times j, sorry. Got ahead of myself. J plus stretching factor z1 times k. And it turns out that these 3 numbers, x1, y1, z1, those are exactly the coordinates of this point up here, right? They're exactly the coordinates of this point. And so the difference between the standard or component notation up here and the ijk notation down here are just how you write it down. It's just a matter of how you write it down. So this is the same. This is actually exactly the same vector as this one, x1, y1, z1 in standard component form. All right, so these are just 2 ways to represent the vector. We will see as we move forward. I kind of jumped the gun with this because we hadn't talked about stretching vectors yet, but that's okay, because when we get to it now, we will already have, motivation. We'll have a reason for wanting to know why this works so well. But you can see that the x1, y1, z1 are the same numbers here, right? Whatever they are. And the I is just a placeholder for the first location. The J is a placeholder for the second location, etc. For K, third location. All right, so I'm going to end this lecture here. Please read the book, watch the rest of the videos, and enjoy this vector conversation.